University of Tulsa said you have to have one. Really? Yeah.
It's good. Take home that lab. Like homework.
As a student, I had a motion controls class, and actually a non-moving controls, but that was the worst one. It was a take-home exam, and I think they spent 4 days, but I got halfway through the problem, and I got farther than anyone else in the class. That was in Parker. It was designed to control it in gear train and backlash. So you had to work out the entire set of equations because when does it disengage, when does it re-engage the gear teeth. That's the problem to solve. I won't do that to you. But it felt character. Okay, so questions? What do you have?
Can we just write down again the equations for the min order observer?
Write them down, I would if I brought them. What I'm going to do, right. I would be able to write that down without.
Yeah, I just have a lot of inconsistencies in my notes.
Okay, let me post those with Canvas. Write them up. It's mostly to calculate is for the, if there's a parallel between the minimum order and the full order observers. And, what's the A matrix for the minimum order observer? Remember, we're partitioning the A, B, and C matrices. So if I have my A matrix, remember, we partition. Usually, we're dealing with one thing that at least one thing I can directly observe, directly measure. So when I partition this, remember this was A, and this was A, B, B. Okay. What was the A matrix for the minimum order observed? ABB. Remember, that's the A matrix of the things I'm trying to estimate. And if you think about that, is the A matrix is the part of the A matrix what I'm trying to estimate. Okay. I don't need to estimate stuff for AA because that's the thing I'm sure about. Right? The known part. So if the part of the A matrix for this observer is the A matrix for the part I'm trying to estimate. What's the C matrix? This is kind of the output matrix for this thing. I should say, no, let's do the B matrix first. B matrix. What's sort of the B matrix for it? The C matrix is B matrix. What's the B matrix? This is kind of the B matrix for what I'm trying to estimate. So what's the input to the thing I'm trying to estimate?
The output of the plan.
AAB.
AAB.
Yeah, it's A. I think A, AB. And then index or whatever. They didn't tell, okay, like observable, controllable, maybe observable. So, essentially the C matrix type thing. So, yeah, what the equations are, I can't remember offhand, but we essentially have to calculate this A hat, B hat, C hat, and D hat. And they have the F and everything, all the other parts, I can't remember what they are. They have those, and A tilde, B tilde, C tilde, D tilde. So this is essentially the observer part, and this is the regulator. Because what happens is that you put the control gains into the tilde parts. And so my regulator is really the state space for the tildes. that is the entire regulator. So this is the plant, output is plant Y, input U, input to the regulator is Y, the output is U. So this thing, that entire thing, the observer and controller, what we call a regulator. I don't know what the proper equation is. One thing I usually do in tests, I don't do things more than set order, because otherwise you just get busy working, trying to do versions and everything else. So things will be set order. Yeah.
And then when designing an observer, the number observer, should we put the system first in observable form?
No, you don't have to. Do not have to do that. This basically takes care of that for you. All right. Why would I put something in controllable or observable form? What's the, what really is the only advantage of that?
It's easier to calculate
It's to calculate what?
the poles.
The gains. It's only to calculate gains. It's the only advantage you get for taking something from a general form, put it into a controllable or observable form. Okay, it is, well, that characterization drops right out very easily, it's just one line. All right, everything nicely separated. But if it's in a general form, yeah, in a sense, we're transforming it to controllable or observable form, and calculating and transforming it back. What are we doing? What method are we using? It's Ackerman's. Ackerman's method really is taking some general form, transforms it into controllable form, calculates the gains, because that's a simple amount of characteristic equation, and transforms it back. It basically took all that transformation stuff, put it into a single equation. And that's what Ackerman's formula is doing. So it said, do I need to transform it to controllable? No, it's already been done. Ackerman's does it for us. And that's only to calculate gains. Right? Once I have the gains, making regulation and everything is the same as any other. The Riccati equation to calculate gains. Finding the regulation is exactly the same, no difference. Just out of the yeah.
But if you, how would you partition your A matrix if you have two known, one known?
I generally like to put them into the first set of the states. So 1, 2, 3, 4. Let's say those two are the known. I will try to make sure that the top ones are the known things I'm measuring. Then the partitioning gets a lot easier. So now I have, this is a 2 by 2, this is a 2 by 2. They're all 2 by 2. You can do it the other way, but then, okay, you know, what's A, B, and maybe these were the known ones, and this becomes A, B, D. And this is A, B, and this A, B, B, and I can start getting confused at that point. So I also put it into this kind of standard form. So this needs rearranging my state equations, that's all it is.
If you only get 3 total states, basically.
Well, then I'm only estimating one of them. So this becomes, that's 2 by 2, this is 1 by 1. That's perfect order.
And then is AAB just the farthest right?
This would be just, yeah, this would just be A, B, and this is A, B, A. So if I put these as the known ones, the partition is always the same. The size of them doesn't matter. But dimensions will work out. As long as you enter them correctly, dimensions work out. Makes no difference. But, say, out of habit, I'll create stuff up here, where those top ones. And it's less confusing, less likely to make a error. Even if the one I measured is that one, X1, X2, and what I've estimated, I'll rearrange my equations so it comes up there. And that's not very good. If your equations okay, rearrange it like that. Top one is my what I've measured. Anything else? Yeah.
We have the microcontroller equations on the test.
Oh, so pseudocode? Yeah, you should be able to give me a simple pseudocode. So here's a difference equation, tell me what the pseudocode is. Or tell me what the missing line is. Something like that. Where is the error in this code? That'll be this in the evil when we do. Never do that. I can't even do that myself. What is the one we had that? Who was it? It was going for error trying to debug your minimum order observer gap. And what was it? Some stupid little.
I had a VA instead of K.
Yeah, go ahead, Pat. All right, it's like, and you're like, I know, looks good to me. It's really hard to debug, especially somebody else's does.
What materials are you going to cover on this test?
Basically, primarily it's design controllers and observers. So be able to, here's the controller I want, given this controller, what observer do I want? In the kind of optimal part, I'm not going to have you solve the Coddy equations, but you should be able to set up a Q&R matrix. Say, I want to penalize statement number 2 by this much stuff. And he says, oh, here's a good Q&R matrix. Use that. Won't have you do a calculation on that because we'll be able to introduce that by running the Reader's Digest version. Here's other things you can do to you have to really to do that, you need to learn some stochastic processes and some statistics. Do a calculation. So we'll and I know everyone's background in statistics is very different. And usually, same color, I know I'm always learning stuff about statistics. Every time we do some experiment on people, we realize that, well, that didn't work, we need to do this one. Back, other questions? Yeah.
Can you briefly go over how to get Q&R for the?
Yeah. Remember, you have to have Q as a positive, R as a positive definite. So it weights the input. So Q weights the states, R weights the input. R weights the input. Nice example is for pendulum. Yeah. I can't remember the order we have for the states. Let's say theta of the pendulum, theta part, omega of the pendulum, omega of the part. Say those are the states. I can't remember what we have in order. All right, for the pendulum, we want to keep that theta near 0 as best I can. Right? So this is going to be a 4x4. So the way I like to do that is when at what's the maximum tolerance I'll put onto that angle. So if I want that within, keeping within 2 degrees, of course I need to convert that to radians, right? So plus or minus 2 degrees, and that is radians, and square that can be the reciprocal of that. So if it's a small number, if I want to keep it within 5 degrees, I'm not weighting it as hard as I want to keep it within 2 degrees. So smaller tolerance here, the bigger my weighting. It's a penalty we're putting on this. I'm trying to minimize these penalties. Okay? Kind of minimize QR requirements. The bigger they are, the more it's going to try to do that. All these others are going to be zero. There's no cross. They're not waiting theta times pendulum times theta part. The part, I might want to keep that centered. Maybe not quite so strong. So again, I will put it mass. What about velocities? If I don't care how fast it goes. Zero. Really, I'm saying the max is right? These would be zeros here. And I can put zeros for those. Means I don't care. I don't care about those. And that's perfectly valid for this. Yes?
Now, if there's like physical constraints on how fast the car can go, do we
I
have-
might do that. Yeah, I might say, well, the motor saturation speed is so many RPM, convert that first radians per second, and say, okay, I want to penalize that because I want to keep it away from that motor saturation. Yeah, so I can do that. Or there's restrictions on the components. I don't want it running too fast because I'm going to burn out the barrier, which is another thing we have. So that would be a point of weighting these things. You might try that last, how much effective that is. So if I don't weight velocities versus I do put a weight on one, what do you think it would do? Just gut feel. If I don't weight velocities versus, oh, I weight velocities, counting on this behavior would be. I'd probably slow down if I penalize velocities. Because, yeah, it might go too fast. So we'll slow the system down. Just gut feel says it should do that. Try it out. You'll see it. We'll do that. The nice thing about that map is you can really quickly try different weighting coefficients out and see the effect of it. So what's the effect of being sloppy here versus being really tight? Right? You know, you can be, we're really loose here, I'm fine. Or you keep that absolutely going, you know, you got the guns at the head saying, you keep that thing balanced. Shape. Okay. So mostly it's like, is there a wrong answer here? For the pendulum, maybe one wrong answer. That would be what? Putting a zero here is probably a wrong answer. Right? Because you definitely want to make sure that thing stays balanced. The part, now that's a rotary system, so the part really can rotate completely around. And then for the R, that's weighing the inputs. What would you do for there? You have to have this one non-zero. Why does it have to be non-zero? It gets inverted in the Riccati equation. R is there's an R inverse. In fact, when you calculate the gains, there's an R inverse. So, what would you choose? 1 watt. And the flat one is a good answer. But what have I really done? One is flat. 1 squared is still 1. Right? Give me some dimensions. Remember one thing we're doing here? We're not dimensionalizing because our penalty function, remember this. X transpose QX plus U transpose RU dt. Right? That's equal P. So X times X is the state squared. This is why we have squared here. Well, X, if it's